Let's now look at some examples of the direct boundary element method. We'll start out with an automobile transmission case where there's internal force unbalance that's making it vibrate and making it radiate sound. A second will be the automotive muffler that we looked at earlier with the finite element method. Let's consider an automobile transmission case. This is a housing that contains the gears that make up the automatic transmission shifting unit. It bolts to the back of the engine, and then the drive shaft comes out of the rear of it. Now this body, although the outside shell is a continuous shell, actually has quite a large opening in the front where it attaches to the engine, and then it has a moderate opening in the back. Those are going to be considered to be closed off in our acoustic model so that we have a interior region that is not of interest separate from the exterior region. We're going to look at this then as a direct analysis boundary element problem. We're going to look at it at a 300 Hertz frequency. The surface velocities on the case of this transmission are found in a mechanical forced response solution using MSC Nastran, and the output of that run, namely the surface velocities on the transmission case itself, are then going to be used as input for the Comet acoustics run. The transmission will radiate noise, which will then be viewed by an external cylindrical data recovery mesh. The automobile transmission is based on an actual transmission, but has been simplified to allow us to do our modeling here. The interior structure has a pair of bearings that support the shaft from the engine and then the outgoing shaft. The load will be applied at that location of the forward bearing. The speed of sound exterior to this transmission case will be assumed 343 meters per second. The air density will be standard as well. Now when we go into our boundary element modeling, there would be several ways to create the mesh. In this problem, the SDRC ideas package was used, and we used quadrilateral elements. The front and rear openings to this case were closed by adding flat plate regions across those faces. Next, I'll show the acoustic mesh that was used. These are the quadrilateral elements that were generated. Notice at the left we have the closing of the opening between the engine and the transmission. You see the engine would continue on in this direction, and that closure appears to be a flat plate here because of the rectangular grid that you can see. On the right here you have the closure where the drive shaft would exit the transmission to the rear of the car. Now, those closures are artificial. They're meant to keep the interior air from radiating sound to the exterior. And so we want to give those as rigid surfaces, and that's done in Comet Vision as shown below, where we've boxed in the relevant elements on the right and on the left. And those will be made stationary. On the remainder of the body, we want to import the velocity data for the actual vibrating engine, and that comes from the MSC Nastran run. The location of the mechanical force, although it was applied to a structural model, you understand, a plate model, would have been relative to this acoustic surface, would have been about here. And it had 1,000 newtons vertical component, 1,000 in and out of the page, as you see here, and then 10 newtons on the axial direction. So it represents a rotating eccentric body, but with some axial component. Those values are peak values as input into the finite element analysis, and they were at 300 Hertz. Let's now step through the solution procedure. We'll start with these introductory steps on this figure. The acoustic boundary element model of the transmission is made using a preprocessor such as IDEAS. Element normals must point away from the fluid region, so they point to the interior of the transmission. We will assume that the structural frequency response problem has been run and the surface velocities are available in a punch file. And the details on how to do that within MSC Nastran are given here. The preliminary work that was just discussed could be done in other ways. One way would be to measure surface velocities experimentally and use that as a surface data. Or alternatively, there could be other preprocessors used for creating the acoustic mesh. But let's assume that those steps are done now. We should import the acoustic model that has been developed into Comet Vision. This is the acoustic preprocessor. Then we define the important views and save those. We create a cylindrical data recovery mesh on the outside of the transmission, presumably representing the observer who's going to be irritated by this noise if it's not properly handled. Then we need to set up a group for velocity interpolation, and we need to bring in the mechanical velocities from our preliminary work, in our case a finite element program, and merge those with the acoustic model. Now this is a general problem that occurs in some other technologies such as aeroelasticity, and there, as here, you may have a different structural model than fluid model, and you need to make a smooth interface between those mesh patterns where they join. We need to assign the material properties of the air, set certain Comet analysis parameters, and then in this Comet Vision run we write out the Comet acoustics data, and that's going to be our main run. So we run that data with Comet acoustics, and then we post-process. And that post-processing could be done with Comet Vision or with other post-processors. The next figure shows how this velocity interpolation is handled. The nodes at which velocities are going to be considered are circled in this figure, and then out of all the total nodes that constituted the model, they're the ones that will be carried into that matching process. And the identification of those nodes here was done in Comet Vision. Then with that actively vibrating surface, we will sketch it and the outside viewing plane here. Notice that the closures at the front and the back of the transmission case have now disappeared. Let me also show the velocity field on the surface of the transmission. This will be the driving force in this problem. I'm using arrows here, and it's not the best way to do it, it turns out. Contour plots are probably a little better to visualize, but it's the only example I'm going to give with arrows expressing the velocities. Remember that this mechanical motion illustrated here came from a force on balance due to probably bearing slop and things like that on the interior of the transmission, and then that mechanical force was transmitted out to the surface through the various partitions and bearing plates and so on that make up the structure of the body. So an external viewer then would see these velocities. The next four figures have to do with the sound pressure levels on the transmission and out on the viewing surface. Here is the sound pressure level on the transmission itself. At 300 hertz, you find that the correlation of the local pressure with the local velocity is not completely correlated. At higher and higher frequencies, it does become more highly correlated, though. So what I'm saying is that the piston analogy, where you get pressure going like rho VC at a surface, is a one-dimensional flow idea. And if this were at a much higher frequency, then we might see exactly the same pattern for surface pressure here as you would see for surface velocity. Now, in my class a year ago at Michigan, I had the students investigate that, and some of them did different frequency ranges, perhaps 30 hertz, 300 hertz, 3,000 hertz. And they found as you got up to 3,000 hertz, then indeed the sound pressure level on the transmission itself was becoming very close to mirroring the velocity distribution on the surface. So it was approaching that sort of a pressure distribution. It was a very interesting exercise. Perhaps some of you wanting to look at that could take the data for such an example problem and try it at different frequencies. In any event, we see that there are relatively high pressures here, that is sounds, around the location where the bearing plate attaches to the sidewall. There's another hot spot at the back here, and possibly having more to do with the rear bearing location. The reference on our decibel scale here is 20 micropascals. Now I will take the same information but show a color fringe plot to give that sound pressure level on the surface of the transmission. The peak pressure obtained with this kind of a plot is within 0.5% of the previous value, so it doesn't affect the extreme values. I would say that this is a clearer picture, a little easier to interpret. Certainly shows the bullseye nature of these more noisy areas. The purpose of a sound survey such as this would be to find what effect that transmission had on the surrounding people and equipment. So a viewing plane that would allow you to back off and look at that noise from some important distance would be helpful. Our surface here is a cylindrical surface, and here I show a contour plot, and at this distance the sound pressure levels are lower than they were at the hot spot on the surface of the transmission, as you would imagine, because any remote point then will be averaging the hot and the cool areas in terms of sound pressure levels on the transmission case, and there may be some favorable cancellation as well. So this time we get a value here of 102 decibels in contrast to the 120 decibels as the peak noise on the case itself. Since the transmission is very, very generally kind of an elongated body, certainly there's an attenuation with distance, and probably should go like 1 over radius in this case, just considering the surface areas that are involved in the either on the transmission case or on the viewing surface. Now let's look at a color fringe plot of that same information on the viewing surface. Here we see the sound pressure levels out at this surface, which is 1 meter away from the axis of the engine. The sound pressure levels are, of course, a little lower than at the engine surface itself. We notice that the hot spots here are just radially outward from the hot spots on the case itself. So this case all makes sense. Earlier in our lecture series, we had studied an automobile muffler using the finite element method. Now we're going to look at that same physical problem again, but use the direct boundary element method. Also, we'll introduce the idea of zoning. Here's a sketch of the mesh, the outer surface of the muffler. As you remember, this was a two-chamber muffler with a dividing wall roughly at the middle, and then with a short pipe connecting the two chambers. We'll look at the pressure drop across this muffler at 500 Hertz, assuming a velocity condition at the entrance and then a far field impedance at the exit. I always like to divide my modeling into physical modeling and then the boundary element modeling. Under the physical model that we've developed, we're going to put a unit velocity condition at the entrance at 500 Hertz. At the outlet, we're going to assume the condition is that of a plane wave interacting with an infinite body of air, and that infinite body of air has a far field impedance of rho c. So that boundary condition is applied on the exit plane. Now, in retrospect, we've also run this problem by a method called the indirect boundary element method, yet to come, and that properly accounts for that exit condition and is not much different than the solution we get here. So we know that this somewhat simplified exit boundary condition is okay. We're going to model the two resonant chambers with the connecting short pieces of pipe. Now, when we go into our boundary element modeling, we're going to use primarily quadrilaterals, and we're going to have a data recovery surface that will be a vertical plane cutting through the center line of the muffler. We've used the preprocessor in SDRC Ideas to create both the acoustic boundary elements and the viewing plane. We will use three zones in describing the muffler. The first is the left resonance chamber, including the entrance pipe with a closure at the end that's planar. The second is the short interconnecting pipe, again with planar end closures. And thirdly, the right resonant chamber, including the exit pipe. Because we can use different material identification numbers, we can create three separate temperature fields here. The element normals are to be pointed away from the fluid field in interest, so they point outward from the muffler out to free space. I'll show you the solution procedure now. We've assumed that we have already created the acoustic model in a preprocessor, and that can be imported into Comet Vision. Then you can define and save the views that you would like. You create groups for boundary conditions, for instance, the entrance and exit planes. You bring in the data recovery mesh into Comet Vision. You apply velocity and impedance conditions at the entrance and exit planes. Assign the material properties for the air in the different zones. Set analysis parameters with the various checking capabilities. And write out a Comet Acoustics data set. Now this will be then imported into Comet Acoustics and executed. The acoustic model has been made in SDRC Ideas in this example, and we'll import those quadrilaterals into Comet Vision. Here's a picture of the acoustic mesh above and then an oblique view below. Within Comet Vision then, the elements are given their properties, the normals and so on, and here's our side view of the muffler. Then you can define the inlet and outlet element groups to give the impedance condition here at the outlet and the velocity condition at the inlet in Comet Vision. We now set the frequency in the data equal to 500 hertz, and in this case we're going to say that there is no data check required in regard to tolerances on the mesh. These typical numbers are shown here, but by setting 0 on this DAT check index, that means that these tolerances won't be enforced in fact. Our data set is now prepared, and we can put it into the Comet acoustic program and run the analysis. The results come out, and then they can be viewed by various post-processing programs or within Comet Vision. We're going to look at fringe plots of sound pressure level on a vertical plane through the middle of the muffler. Here we can see what's going on due to the unit value of velocity at the input side. And we see that the first chamber, of course, is relatively more noisy than the second, which has the cooler and darker colors corresponding to the bottom of our sound scale. The peak decibel rating for this body is some 86 decibels at the entrance level. At the exit level here, the numbers are closer to the 50 level. So there's been a substantial reduction from start to finish. An interesting conjecture would be that if this muffler were to only be used at 500 hertz, then this would be the wrong position for the outlet pipe, because you would much prefer to have the outlet come to the side here. But as mentioned before in our finite element run, we know that mufflers like this have to have a broad range of frequency suppression. And so therefore that's not done. And I imagine manufacturing is quite a factor here as well. But it is interesting that the muffler design such as this is a relatively effective quieter of incoming noise. And of course, a major part of the comfort in modern automobiles is that the engine noise is suppressed so thoroughly.